So in summary, what we have is what we call I, the moment of inertia, also called the angular inertia or rotational inertia. And this is simply the resistance to angular acceleration, alpha. And it does turn out that what we just showed is that if you just have a mass out in space, the moment of inertia of that mass will be mr squared, where r, and this is super important to memorize or learn the rap of it, r is the displacement from the axis of rotation to the point where the mass is stationed. So in this situation that we just drew up, the system moment of inertia is m1r1 squared plus m2r2 squared. Now let's go ahead and do a simple example where we have to do some calculations on this. Got a 5 kilogram mass right there, 0.2 meters away from where I'm going to be holding it. So we got to figure out what the moment of inertia of this thing is. I equals mr squared. That is 5 kilograms times the displacement from the axis of rotation. This is r right here. It is a vector. And that is 0.2 meters. 0.2 meters, and I square that. And when I do that, I get I equals 0.2 kilogram meters squared. Notice the units on that. That's I of this thing right there. Now, let's go ahead and find the moment of inertia of a 2 kilogram object. Let's say I'm holding it right here, and half a meter away right here, so I'm holding it right here. I'm going to be spinning it from this point. Here's my axis of rotation where my left hand is. Right over here, there's going to be a 2 kilogram object right there. So how difficult is that going to be to rotate, to accelerationally rotate it? In other words, to give it some angular acceleration. Well, all I got to do for this one is do the same thing. I equals, for this guy over here, I is going to be equal to its mass, 2 kilograms, times r squared, which is 0.5 meters quantity squared. And when we do that, notice that we get 0.5 kilogram meters squared. Moment of inertia of this is greater than the moment of inertia of this one right here. Notice that and I'll show you the r vector as well for this one. Here's r. There's the r vector for that one. Notice that the r really makes more of a difference because it's r squared. So that really makes a big difference. What is the moment of inertia of this system when they're both on there? Well, if you guess that is just the sum of those two, 0.2 plus 0.5 kilogram meter squared, you'd be right. Just like masses, these moments of inertia just add. So if I was holding it right here, I had my 5 kilogram mass right here, and my 2 kilogram mass right out here, this difficulty to angularly accelerate would be 0.7 kilogram meter squared. Now for solid objects, this varies for different things, but you can see that depending on the shape, they might have more or less moment of inertia depending on how far away all the mass is from the axis of rotation, and depending on what the axis of rotation is. Now a hoop, this is the one you have to know. If it's a hoop, a dimensionless hoop, in other words, all the mass is exactly r away, and it's got mass m, it's just like a bunch of little tiny masses all a distance r away. As you could probably figure out, for a hoop, the moment of inertia is just m, the total mass of the hoop, times r squared, the radius of the hoop squared. I equals mr squared. This also works for a tall cylindrical shell. As long as it's all the mass is in this very thin shell, doesn't matter how tall it is, all of it's still r away from the axis of rotation, and this is rotating about the center axis. That is important. This is only true about its central axis. I is mr squared for both of these. So here is I for these guys right here. For a hoop or a thin cylindrical shell, I equals mr squared. Those are the only ones that you have to know by heart. There's some useful ones that you can know by heart. You don't have to, but it actually can save you especially in the C class, if you are unable to integrate very well, by memorizing it, you can actually get the right answer. But for a disk, you can see that a lot of the mass of the disk is no longer out here. This is like a solid disk, something like this thing right here, solid disk. Because there's less of the mass on the outside of it, it's actually less moment of inertia. I equals 1/2 mr squared. We will derive that with the C kids. So for a solid disk, not a hoop, but a disk that's got all of its mass distributed, less of it's farther away from that axis of rotation, which I'm going to just emphasize is right there. Here's the axis of rotation. Or of a solid cylinder, 1/2 mr squared. For a sphere, it's 2/5 mr squared, harder to derive. For a rod about its center of mass, the moment of inertia for a rod, that would be just like this, about its center of mass is 1/12 ml squared, where L is the length of the rod. And that will also change if you're rotating about this end. It's a different moment of inertia. And you might guess, well, is this going to be greater moment of inertia than this or less moment of inertia than this? Well, if you notice that this situation has in common with this, it's got like half of the meter stick away from the axis of rotation, but then we have this that's farther away. Turns out that rotating it like this is 3 times as difficult. Rotating it, trying to accelerate it rotationally is 3 times as difficult from this end as it is right from the middle right here. And we'll calculate that with the C kids.